lecture was one of the more important ones in the sense that we covered a lot of ground. So I just wanted to very quickly recap what all we did. So did a bunch of things. The first one was Markov's inequality. So this is a simple inequality, but it says that if you have any random variable that takes non-negative values, it cannot be too much larger than its expectation, okay, with reasonable probability. So it says that that informally probability that random variable is too large, more than some factor, right? some t times the expectation is less than 1 by. So I have it on the next slide, so this short. Right, so it is yeah. So the probability that it's more than some number t times the expected value is at most 1 by t. Okay, and this we said is very useful because now when you're talking about, when you're trying to analyze an algorithm, it makes sense to just look at its expected running time or things like that. Okay? And Markov's inequality can tell you that the probability that you take much longer than that is bounded. Okay? So that's what we saw, and we also saw that Markov's inequality is weak in that it doesn't give you a very strong bound on something like this. It just tells you that, for example, the probability that your random variable is more than 100 times the expectation is less than 1 by 100. But if you want a much tighter bound, then you don't get it from Markov. But often a weak bound is enough, because even if you have something that succeeds with probability a half, you can repeat it multiple times, and then your probability of success just goes up exponentially. So that's what we saw last time. And then we started looking at this question of, motivated by hashing, we started looking at this question of throwing different balls uniformly into a bunch of bins. Okay, so we had some n balls which we were throwing into m bins, okay, all independently, uniformly at random. And we were interested in various statistics, right? Like we were testing, for instance, things like what are the expected number of balls in each bin, and so on. Right? And we said that, yeah, and in the process we came across a bunch of very useful analysis techniques. Okay? One is this notion of defining appropriate random variables. Right? So we said that this was somehow very important, right? So we said that to analyze what's going on, we had to define certain appropriate random variables. Sometimes we expressed a random variable as a sum of much simpler random variables. So what you will find is that in most of randomized algorithms, if you want to analyze them, defining the right random variable is kind of a key to doing. Okay? So that's something that you have to keep in mind. That's something we saw first examples of last time, and then we said that the expected value satisfies this linearity property, which is that the expectation of a sum is the sum of the expectations. So, and this is again something that's very useful in analyzing that. Okay. And the final thing that we kept seeing, so this maybe we didn't state it explicitly, is that expected values are easy to compute if the random variables are binary, and otherwise they can be somewhat of a mess to compute. Okay. And so one thing we kept doing last time was to write whatever random variable you're interested in as a sum of binary random variables. Okay. That is ones that only take 0 or 1 values. Okay. So that's something we did last time. All right. And yeah, so this is Markov's inequality. One thing I wanted to note here is that Markov's inequality does not give you any bounds on whether some variable can be much smaller than its expectation. Okay, on the probability that random variable is much smaller than its expectation. Okay. So for instance, if you have a random variable whose distribution looks like this, Now this is the expected value. Okay, so this is let's say C. Now Markov's inequality only tells you talks about the probability of it being much larger than this. Okay, so it says things like the probability that you are beyond a certain value out here is small. It doesn't tell you that, for instance, probability that you're here is small or anything like that. Yeah.
If we know the distribution is symmetric, can we use?
Yes. So in special cases, you can use Markov, but in general, this doesn't say anything. So you could have So this is, let's say, 0, and you can have some distribution like this. Okay. Note that this is a non-negative random variable, so it's beyond 0 it goes down to 0. All right, so this is something that some people asked about last time, and so this is a good thing to remember. It also doesn't tell you, for example, that there is enough mass out here. So it could be very tiny mass out here. So that's another thing. Okay, so this is something small. All right. And what's the plan for today? So today again we'll cover a few very useful things. So first we will answer one question that we had left last time about the balls and bins process. We'll see how that. I'll have a few thoughts about hashing. And today one of the very useful ideas we will see is this notion of a union bound, which I'm sure all of you have seen in some form. It's intuitively pretty clear, but we will formalize it and call it the union bound. Okay, and finally we'll start talking about some sampling. So probably in the last half hour. Okay. Okay, so actually, any questions about last time before we move on? Okay, so these are the few questions we start off with, and we said that suppose you have n balls which are randomly thrown into m bins independently. We said that the expected size of each bin is m by n, and we were specifically interested in this case when n is equal to m. So most of last class we kept looking at this m equals n case. And in this case, the expected size of each bin is 1. Okay, so when but then we said that in spite of that, there are a fair number of bins that have larger than one element. Okay, that have more than one ball in it. In fact, we did this computation. We said that suppose you ask what is the expected number of bins that have exactly 4 balls. Okay. So we found out that probability was approximately some n by 65. Okay, so I think I wrote 80 last time. That was a bit of an underestimate. But this value turns out to be something like this. So this is a fair number if you think about it, right? This says that constant fraction of the n bins actually have 4 elements or larger. Actually, this is exactly 4. So, right. And so today we want to see a generalization of that. We want to ask, what is the probability that there is a bin with lots of balls, right? Like what they're saying is that it is pretty common to have bins with 4 balls. Maybe it's common to have bins with lots of balls. So could this happen? Right. So that's what we want to see. So any questions about what we are trying to see?
Minimum number or this is the exact number?
Yeah, so let's say I actually have bigger than or equal to log. Okay, so it should not matter, but yeah. Yeah, or to make our calculation easier, let's just stick to exact number. It will be the same. Yeah. Okay. So this is what we will see. All right. So one thing that you should remember is that you should feel confident about defining random variables. Okay, like if you want to know the probability that there exists a bin with log n balls, what is the natural random variable you will define? It is basically that, right? So define a random variable x, which is number of bins with log n balls. Okay. And again, x you can write it as a sum of random variables, because the standard picture we have a bunch of going into equal number of bins. And so this is the quantity we are interested in. And formally, what are we asking? We are asking what is the probability that x is bigger than or equal to 1. What is the probability that there exists a bin with log n balls? That's the question we're asking. So it's just what is the probability that this is this? Or equivalently, it's like saying what is the probability. So this is 1 minus the probability that x is 0. This is x is a non-negative random variable, so it's because it's a number of things, and so the probability that it's more than or equal to 1 is exactly the probability that it's 1 minus the probability that's equal to 0. So these are all things that follow immediately from the definition, and then like last time we can define xi. Let's go to yi. Different from this. Okay, so yi is, let's say, this event, and just like we saw last time, so you have by definition x equals y1 plus y2 to yn, because the number of balls and number of bits are both equal to n. Okay, so this is what we have. This is just by definition. And we are interested in that quantity, right? So the probability that xi is bigger than or equal to 1. Okay. So, so one thing you can do is you can ask what is the probability that one of them is equal to 1. And in terms of that, can you write that probability? Can you express the probability that we have on top in terms of something about these random variables, y1 through yn? Maybe not the final answer, but something that would allow you to start expressing.
So we should consider x equals to 0.
Okay.
1 minus.
So
and x in the bottom equation. So we should consider case that x equals to 0 because it's might be 0 right now. And it turns out that x equals to 0 is also equal to 0, right?
okay, so what he is observing is that the only way capital X can equal 0 is if each of the yi's is equal to 0. Okay? Or if you want the complement, the probability that X is bigger than or equal to 1, you can write it as probability that y1 equals 1. Or, so this is a symbol for or that maybe most of you have seen. Yeah.
You wrote yi as the probability, but don't we really want it to be the event where all I was?
Sorry. Yes. Yes. The random variable that indicates yeah, this makes a big difference, so you should note this. Okay, so yi is always a random variable. It's a binary random variable, and it indicates if bin I receives. Okay, so this is what is exactly the same as last time. Okay. We always define one random variable, which is x, as a sum of simpler random variables, and in this case, this y is a simple random. And right, and then we have probability that x is more than equal to 1. There's probability that y is equal to 1 or y2 equal to 1. So even if one of them is equal to 1, then your x would be bigger than equal. Okay. So this is what we want to look at. So now, how do you analyze the OR of a bunch of events? So if you want the probability that something happens, like event 1 happens or event 2 happens, yeah. So right, so you might think that this is it equal to the sum? Let's start with equal. Yeah, so it's yes. If you want exact inequality, that's something else, so we will get to that. So it turns out that this is equal to probability that y1 equal to 1 or y2 equal to 1. Okay. And this general result, so this is what is called the union bound. So it's a very simple result. It basically says the following. So suppose E1, E2 to En are events in some probability space. If you don't know what probability space is, it doesn't matter, they are just some events. Okay, so then probability of this event E1 or E2 is less than or equal to sum over probability. So this fact is known as the union bound. Okay, and so this is tied, becomes equality. When do you think this becomes equality? Yeah, so not independent, if they are disjoint. Okay, so the probability that so E1 and E2, for example, should not co-occur at any time. Okay? And that makes intuitive sense, right? Because if you're looking at E1 or E2 happening, and let's take the extreme case when E1 and E2 are the same. Right? So in this case, whenever E1 happens, E2 also happens. Okay? So then the probability of E1 or E2 would be basically the same as probability of E1. Okay? Whereas the right hand side is like 2 times probability. So in the case when E1 and E2 are the same. Okay? So if you want this kind of thing to be tight, then you don't want overlaps between these events. So it becomes equality when if and only if EI are all disjoint. So EI and EJ equals 0. For all. Okay, so this is when we say that they are disjoint, when EI and EJ never happen simultaneously. And in fact, this kind of a thing is part of a more general formula. So this is called the inclusion-exclusion formula, where which holds actually for any events, and it's an equality. So it says that probability. Let me write it for n equals 3. Okay, so this is something like probability of E1 minus probability of E1 and E2 probability of E3 plus probability of. Okay, so in general, the formula looks something like this. Okay, so it's like you have these first order terms, and then you have minus, and you get these second order intersections, and you get plus these third order intersections minus fourth order. So, okay, so it has alternating signs, and this is always an equality. Okay, this inclusion exclusion formula is an equality. Actually, how many of you have seen inclusion exclusion formula? Okay, so most of you have seen it in some probability class, right? So you can imagine that this follows from something like that if you want. Okay, so yeah, it is also easy to see otherwise, but if you really want it, you can follow something like this. Okay. So in fact, sometimes you can get tighter forms of the union bound where you have, like now imagine you want a lower bound on probabilities, right? So then you can say that, suppose I want this thing is bigger than or equal to something. Okay? Then I can take the first 2 terms of this expression, and I know that the left hand side is only bigger than or equal to that. Okay? So that's the reason, even though people normally just use the union bound, sometimes it makes sense. In fact, in one of your homeworks, you will do something of this kind, okay? Where you will stop. Like what you will see here, at least in the analysis that we do, is that you'll only get an upper bound on the probability that a bin has log n elements. Okay. So it won't tell you whether this is matching with if this upper bound is tight. If you want a tight upper bound, then you have to do a bit more work, okay, which you will see later. Yeah.
So in this case, we are assuming that it's not disjoint, right? The probabilities.
Yeah. So this holds for any events. Yeah. For all events. Yeah, so both the statements hold for all events. I just said that it becomes equality if EIs are all disjoint. Alright, so any questions about the statement of the union bound itself? Okay. So it's a very simple bound, but it's a very useful one. Okay, so as we will see. All right. So now this is what we used here, right? So we used the union bound in this step to say that probability that x is more than or equal to 1 is at most the sum of all of these things. Okay. But now these are all symmetric random variables, right? Like y1 is the same as y2, is the same as y3, so on, because all bins are equivalent. Right? So all bins are equivalent, therefore so all bins are equivalent. This way. So this one. So all of these terms are the same. So in particular, it's enough to only look at one of these terms. Okay, so let's now look at one of these terms. Now what is probability that sum y1 equals 1? So yeah, and let's look at a more general question. What is the probability that one bin has k balls? K equals log n is what we are interested in. But let's look at a more general question. So this is something we saw last time. So do you guys remember how we analyzed this quantity?
1 divided by
Yeah, so this was the calculation where we did when we had k equals 4, right? So we said that you want, out of all these n bins, we want n balls, you wanted 4 of them to go into bin 1, and we wanted everybody else to go into bins that are other than bin 1. So this is how we did this computation, right? And we did this for every choice of a 4 tuple, right? So you can do the same thing now. There was nothing very sacred about 4. You can do it with any k. So that's what we can do now. So this is something like, so this is exactly equal to n choose k, which is the number of k tuples you can choose, times, you want everyone in that k tuple to go to exactly to 1, right? So that happens with 1 by n to the power of k. And you want everybody outside that k size set to go to something other than. So that happens with n minus 1 to the power of. Alright, so this was somewhat nice to do for 4. For k, it's a bit more messy to do, right? I mean, as you can see. So, does anyone have a guess on how to approximate or analyze these kind of things? You've seen.
System is less than or equal to 1 by 2.
Right, so yeah, so the last term you can play with it and say that 1 minus 1 by n to the, n minus 1 by n to the power of n is roughly 1 by e. So that's something that maybe some of you have seen. But I was more concerned about the first term. Right? So the first term is it involves some factorials and so forth. So how would you estimate this? So this is, so let me write out a basic fact which is commonly useful in these kind of computations. This is called the Stirling approximation. So this is specifically for factorials, but I will write it down for these binomial coefficients. So this is the consequence of Stirling. expression, which is that n choose k turns out to be less than or equal to n times e divided by k whole power. Okay, so this is a very useful fact when you are dealing with these kind of things. Okay, so it's yeah. And once you plug that in, this expression becomes nicer. So now you have this bound is less than or equal to n t by q by n minus 1. Yeah, so again, let's cancel out the n. Okay, so it would have been n here, so I'm cancelling out one of the n's. So this is the bound you have, okay. And this term, like he observed, is let's approximate it by this. Let's say that this is less than or equal to 1 by e. So overall, you get that this term, actually it's not less than or equal to, but let's say that it is approximately this. Okay, so yeah, let me be a bit hand wavy here. Trust me, this is true. Okay, so I mean, what he said is yeah. So 1 minus 1 by n is less than 1. So yeah, you can't use that exactly as a bound, but it's roughly a bound. Okay. So this is approximately that. So the overall thing would be less than or equal to. So the point I would like to make is that this is less than or equal to something that looks like 1 e by k to the power of k. Okay. There's some constant here which I have not. All right. So now, what is the point that I'm trying to make? So this quantity, it reduces exponentially, or something even larger than exponential, as k grows, right? Because imagine k equals 100. Right? So E is some fixed quantity. It is some 2.718. So what we are saying is that this is something like so this is something like 3 by 100 to the power of 100. Which is an extremely tiny quantity, right? So when k is even when k is 100, this is some tiny number to the power of 100. This is much smaller than 1. Okay, so that's the point I was. Last time we saw that for 4, this was actually a reasonably big quantity. It was like 1 by 65 or something. But for large, as k grows, this number really drops. And that's what it is. So any questions about what you've done? Just assume that Stirling approximation holds and these calculations work out. But about the message, which is that you have this probability, this goes down as something like e divided by k whole power. So that's what you need to understand. Yeah.
Do we have to assume that k is pretty small?
For these approximations, no.
Okay.
Yeah. So Stirling approximation holds for any k and any n, as long as k is less than n. Yeah. Yeah.
Yeah. K equal.
Yeah, so for, I mean, there are constants that I didn't write.
Yeah, constants.
So, yeah, I think there's a 1 by e or something that you have to add if you have to be extremely correct. Yeah. Right, so, okay, so that's a bound we have about y1 being equal to 1. So if you set, right, so now what you have to do is what happens when k is roughly log n. So we are interested in k being log n. Right, so what is now you are interested in this e by k power k. And this, if you think about it, so this is something like and log n is something that grows with n. It is a function that grows with n. So, and e is some fixed quantity. So you can imagine that for large enough n, and this e by log n vanishes. So this becomes less than whatever you want. So let's say it's less than 1 by 10. And now this bound already tells you that in this case which is less than 1 by n squared. Okay. So I'm just giving you a very conservative upper bound. Okay, and this is okay, so again, this is straightforward math. If you don't understand, it doesn't matter. So this is a straightforward calculation. Yeah.
But this is for one bin, right?
This is for one bin. That's why I want. But the point is that I want to get a bound that is like 1 by n squared. Okay. So I mean, you can verify these computations. Okay. So all right. So what I'm saying is that the probability of y1 equals 1 is less than 1 by n. So why did I do all this and get a bound like this, right? So the point is that now if I take a union bound over n different events, this is still a vanishing quantity. Okay. So if you now take a union bound, so imply probability that y1 equals 1 plus probability of y2 equals 1 probability of yn equals 1. This whole thing is less than or equal to n times 1 by n squared, which is still negligible. Okay. So that's the reason I wanted to get a power of n here, 1 divided by power of n, so that this n cancels. Okay. So that's why I did all this manipulation. Okay. So the conclusion of all this is that you can now plug this back into the original, and you can argue that the probability that x is more than or equal to 1 is actually less than 1 by n. Okay, so yeah.
Yesterday, we didn't use this union bound. Instead, we looked at it in terms of the expected value, right? That
Yes.
the expected value of x is equal to the sum of the expected values of y.
Yeah.
Why can we not do that? Or why did we not do that?
Oh, so you could have done that. You could have done the expected number of things that are equal to, yeah. So the expected number of yi's are equal to 1, something like this, and then you can use the exact same formula. And this one you will get it to be equal to n. Sorry, 1 by n. To be rather. Yeah, let me also do that, because that's also a valid thing to do in this case. But the reason I did it separately is because I wanted to illustrate the union bound. Okay, but that's a good point. So let me do that. So, but first I would like to make sure all of you understand what I did right now. Right. So what I did is started out with this quantity x, which is the number of bins with log n balls. Wrote it as sum of simpler random variables, okay. And then we said that probability that x is more than equal to 1 is the same as probability that is the OR, probability of the OR of all of these events. Then you use union bound to have something which is the sum, okay. And then we are bounding each one separately. Each one we bounded by 1 by n squared. Okay. and so the overall sum was bounded by 1 by n. Okay, that's what we did. Now, what Frost is asking is, why didn't we do exactly what we did last week, like yesterday, right? A couple of days ago. Right? So we know that x equals plus yn, and we showed that probability of y1 equals 1 is less than 1 by x squared. So this means that, this in particular means that expected value of y1 is also less than 1 by x squared. And this means that expected value of x is less than or equal to 1 by n. Right? So far it's all straightforward. So I use linearity of expectation to say that expected value of x is actually equal to sum of the expectations of all these guys. And now I can use Markov to conclude that probability that x is more than n times expected value of x. This is less than or equal to 1 by. This is like the t that you have in Markov. So this is 1 by t. And this is equivalent, if you think about it, to probability that x is more than. Okay, because expected value of x is, it's not true, because it's an inequality, it's not equivalent, but this implies the probability that x is more than 1 is equivalent. Okay, because the expected value of x was something that is smaller than 1 by n. Okay. So you get something like that. Okay, so this is an alternate way of getting the exact same bound that we got before. But it's just that, I wanted to illustrate union bound, which is something that is also very commonly applied. Right? Yeah, in fact, so most things you can do in probabilistic analysis you can do by appropriate Markov's inequality. Okay, so it's even the more complicated Chernoff bonds and so on, you can just view them as Markov's inequality applied to appropriate functions. Okay. So in that sense, the fact that there is proof like this should not be surprising. But there are cases in which looking at the union bound simplifies computations a bit.
That inequality is 1 by n to get 3, not n yet.
Which one?
The last one. Probability of y1 is equal to 1.
Yeah.
We can get 1 by n to 3.
Yeah, you can get whatever you want, because it's actually log n power log n, right? It's 1 by roughly log n power log n, which is actually asymptotically bigger than any polynomial you want. It's just that you want at least n, so that's why I have n squared. Yeah. Alright, so far I have shown something which seems fairly natural. So I have shown that the probability that there exists a bin with log n balls is quite small. This is actually less than 1 by n. Okay, and we have seen two different proofs of this same thing. So it's pretty unlikely that there exists a bin with more than with something like log n difference. And this it fits into this narrative, right? So in some sense, the expected size of each bin is 1, and there are some bins. There's some number of bins that have 4 or 5 balls, but no one has too much. Okay, so no bin has more than log n with a pretty good draw. So the general story of balls in bins when n equals m. Now you might ask, this is only an upper bound. Okay. So is it actually true that there are bins that have something close to log n? Okay. So it turns out that that is unfortunately true. Okay. So this is actually close to the expectation. Okay. So in fact, right. So all of these bounds are fine. And this we said is less than or equal to 1 by n. And it turns out that this is actually close to the expectation. So if you do a random balls and bins experiment with n balls and n bins, it turns out that there is a bin that has something not quite log n, but something very, very close to log n. Okay, log n divided by log n bins. Okay. So it turns out that typically there exists a bin with and by typically I just mean with high probability. With probability at least like 3/4 or something like that. You will always find one bin that has lots of balls. Okay.
Yeah, as you said, we can use the one with 1 over n to the power, for example, p.
Yeah.
For every p.
Yes.
Everyone.
Yeah.
So in this case, when p is large,
Yeah, exactly.
large, it means probability is 0. Why we can find this?
Oh, so yeah. So we can come to that in a little while. So I mean, we can discuss this offline. It turns out that p equals log n is the most you can set, and then everything becomes tight. And
Factor probability is 0, yes.
sorry. No, if
is 0 because you can use 1 over.
so, what he's asking is, here I have this e by log n for log n, right? But if you set k to be equal to log n by log n, then e by k power k would become a constant. And k is maybe not constant, maybe it would become polynomial, but it would actually become something like 1 by n or something like that. Okay, and you can make it become like 1 by root n if you want, and then it will tell you that there are root n bins that have k balls, where k is that log n by log n. And that's one way to see this. So in expectation there are root n. So yeah, so we will not get into that. So this is so again this is it involves a bit of calculations, and it's not that insightful to actually do the computation. I mean, it's useful for you, but I don't know if it's worthwhile doing in class. Okay. So, but what you should know is that that typically there exists a bin with something like log n by log n balls. And if you think about it, this is now bad news for hashing, right? Because what this implies is that if you now hash a set of n elements into memory of size n, okay, then it's saying that there are hash buckets that have something like log n by log n elements that have that bucket. Okay, even if you did perfectly random hashing. Right, so you had n elements in some universe. You are uniformly randomly hashing into like n buckets, and it's saying that with high probability you'll have one bucket that has something like log n by log n. Okay. Which means if you're doing some linear probing or something like that to find if an element exists in your set or not, then you might have to end up taking something like this time. Okay. So this is actually something very useful in practice. So linear probing takes roughly log n amount of time in the worst case. Okay. So there are some bins for which linear probing can take a long time. Okay. But there are nice things you can show. You can show that for most elements, searching for them takes only constant amount of time, so the expected times will be constant and so on. But there can be some elements for which you actually have to go up like log n by log n amount of time. Yeah.
But even if n is like 10 to the 10, wouldn't that just be, like if you're using log base 10, wouldn't that just be like 10 over 1? So,
Oh yeah. So I mean,
so it's like pretty
sure.
small stuff.
If you're okay with something like log n, this is fine. Yeah. So this is right. These are all logs to the base e, so things will be a little bit high. But but this number will never be more than 50 or something. So yeah, 50 is even an exaggeration. So maybe 20 or something. Okay, so this is not a huge value. In practice, it will be about 20, 25, but it could still be a factor you would like to avoid. Okay, so this is probably why, I mean, this is one reason why people often, when you're hashing, you don't just, you don't have a memory, you don't have number of buckets exactly equal to the number of elements you expect. You take a little bit more, okay, so that you have some slack, and then this bound becomes a bit nicer. Okay, so in fact, this is a good exercise for you to do. So if you want your max load to be something like 4, it turns out that you need a size of something like n to the 5 4. So if you have a memory of n to the 5 by 4, then almost no bin will have more than 4 elements. So this is the sort of thing that one can show pretty easily. So, all right. So any questions on these first two things? Because I think those are more interesting. So these are just some kind of birthday paradox type computations that you can do. Okay, but yeah, but it's useful to understand that that linear probing in the worst case can take some of this. And so there's, yeah.
The maximum size of bin is for at least one bin.
For one bin, yeah. A typical bin will actually be much smaller, like I was saying.
So we don't know about the second maximum.
Oh, right. So yeah, actually there's a lot of study on this. As you can imagine, it's a very simple process. So people have studied everything you might want to know. So there are, you can actually draw the distribution, and it looks, and you can characterize it. At some point, it is something like log n by log n. It goes down to 0. The number of bins goes down to 0. Everything else, the short answer is that it looks, the number of bins with k things looks very much like this function 1 by k to the k. Okay, and this decays to 0 if k is more than log n by log n. So yeah, so it looks something like that. N times. So yeah. Alright, but the other nice thing that I want to say is that, okay, so random hashing is nice. It's very natural, and it has that kind of a bound. Now you can ask, if you have n balls and n bins, is there a cleverer way of hashing? Right. So, and there is a very nice procedure. So this is by I forget who the others were, but this was in the early 90s, and this is the school idea which is called the power of two choices. Okay, so how many of you have heard of this before? Okay, so if you haven't heard it, maybe I should describe it. So nobody has heard that, I will describe it. So if you want to hash n elements into n buckets, okay, and like we saw, a random hash function has some bad property that some bins are overcrowded. Okay. So now suppose you do the following. Okay, so you have two hash functions, h1 and h2. Okay, so h1 and both of these are random hash functions. So that means both are like a balls and bins type process. Okay, so every element goes independently to one of the bins. Okay, so both of these are random hash functions. And now, let's say you construct a new hash function h prime. This is and you define it one by one. Okay, so for integers 1, 2 up to n. So n and so 1 you hash it using, let's say, h1. Okay. And now each time when you want to hash, let's say, element I, look at h1 of I and h2 of I. Okay. h1 of I is some bin and it has some elements of I. h2 of I is some bin and it has some other elements of I. And put I into the least crowded bin, okay, of those two. So each bin will have some size, and put it into the smaller one and break ties arbitrarily. So h prime is defined consecutively. It is the I'm using this in front of h1. Right, so clearly it depends on the order in which you are doing, and we are doing it in the order 1 through n. And you put so you put I in the less crowded bin, and let's say you do this from 1 through n. Okay. Now, what would you guess would be like the maximum bin size if you did this? If you just had one function, each time an element comes, you use that h1 and you put it, then we said that there's a bin with log n by log n many elements. But now if every time some new element arrives, you look at two different hash functions and put it in the less crowded one, then it turns out, and this is a very, very non-trivial proof, that the max bin size is actually log n. And for most practical n, this is significantly better than log n. It's basically a constant. So, yeah.
Don't you run into an issue when you need to look up the element? Because then you don't have a deterministic function.
Oh, right. So, but you know, right. So what he's asking is, when you have to look up an element, don't you now have to spend more effort? But you know, if you think about it, it's either h1 or h2, right? So it's just 2 times more effort. So if you want to do linear probing, you would do linear probing twice. So you would look up 2 different bins, but you know, each bin is only log n in length. Okay, so you get 2 times log n as opposed to log n divided by log n. Okay. So that's the cool thing that this, and this is often called the power of two choices, which is that when you're hashing, if you look at two hash functions and put it in the less crowded bin, and this people use all the time in industry and so on, especially when you have these huge sets over which you want to do hash tables, you often take a couple of them and you make sure that there are no collisions this way, okay, that these bucket sizes don't go too much. So, in fact, when you do like a search query on Google and so on, it will not and it has to determine which machines it should go to. Often they do tricks like this. They try to take multiple hashes and then send it to a machine that is more free at this point. Okay, so this general idea is actually used a lot in practice. Yeah.
Use the expansion, can you get also double?
Yeah, so this is a great question. So this is like a true mathematician question, right? So can you do this further? Can you get like 3 logs or something, right? So it turns out the answer is no. The fun stops at 2. Okay, so if you choose b different hash functions, okay, then you only get something like log n divided by log b. Okay, so it is not significant enough that you would like to use 5, let's say, because remember, like he pointed out, if you use 5 different hash functions, now your probing time grows by a factor of 5. Okay, so that's yeah, it's a great question. Yeah, people initially were wondering, I mean, do you get 3 logs or something? All right, so that's great. So now this is the general story behind this power of two choices. So again, so far, so this balls and bins process is like an idealized version of hashing. Okay, because when an element comes, you are assuming that you can hash it uniformly into the bins you have. But actually, if you go back, this is the picture we had about hashing from last time, right? Which is that you have this universe of keys, and once a key comes, you have to hash it into. Your hash function should compute it into one of the buckets. So this can actually be tricky in practice, because the way we have been doing this, we had this H which was taking some element of the universe, some x in the universe, and just computing h of x. This is uniformly random thing. But note that when you're doing some hashing, this has to be some function that you compute using, let's say, this string, right? And it is some deterministic function that you have to compute using this string. So yeah, so and this you have to do it without knowing what the hash values are for the other guys. Okay, so this has to be totally independent of the other elements in this universe. And so computing hash functions is often a tricky thing, because and people often do it by breaking this string up into small chunks, and then you can't afford to have any kind of a lookup table that says, oh, for an x I store the hash value, and then if I want it I look up, right? Because then looking up itself takes a lot of time. Okay, so how you compute hash functions is actually a bit of a tricky business. So usually you have a lookup table for every letter or something like this, and then you add those hashes and do something. Okay, so in your homework you will see one example of a simple hash function, which people, I guess, back in the day they used to use. Nowadays they are much more sophisticated hashing functions. And yeah, so in general this is a very nice, yeah, there's a lot of work in this area. Alright. Okay, so this is generally what I wanted to say about balls and bins. That it's, and in general about hashing. That often, yeah, so if you do just a one-step simple hashing, some bins could get crowded, but there are not too many bins like that. And one way to resolve it is via this power of two choices type thing, and okay. Okay, so the next thing we will do is this notion of sampling or estimation. So this is another the canonical. So this is more of a statistics question rather than a randomized algorithms problem. So we won't spend too much time on this, but at least you should understand how people, how one would go about analyzing this. Okay. So, and it uses the same tools that we've been seeing so far. So it's also a good application of those methods. Okay. So what is sampling estimation? Okay, so let's say you have an array A and you have n elements, okay, and each element, actually sorry, I should have put minus 1 1 because it becomes nicer. Okay, so and each element is in the interval minus 1 1, let's say, and your goal is to find the sum of all that. Or if you like it, let's say the average of that. Okay, it's the sum divided by. So the natural way to do it, the most basically the only way to do it exactly is just linear time, right? You have to add all the elements, because otherwise, if you don't look at all the elements, you cannot get an exact sum. So that's the only way you can get an exact sum. But suppose you're okay with a little bit of error, right? So you're okay with an error of something like 0.01 times n. Okay, so the range of the sum, note, is something like the sum ranges from minus n to n. So this is the range of the sum. So 0.01 n is not too big compared to the range of the sum, right? Many of you seem not to buy this assumption. Why not?
Isn't the range minus 1 to 1 plus? So
range of each element is minus 1 to 1. And so the sum of all the elements, maybe I should have written the average, then it would have been easier to buy the fact that it is an error of 0.01. Okay. So this is the same as saying the average has to be estimated to an error of 0.01. So this is a question you'd like to start with. Okay. So any thoughts? We are studying sampling, so sampling has to be the answer. But how would you try to solve something like this, right? So remember, this is like totally unsorted. It's just some arbitrary array, and the fact that you can do something like this in a very small amount of time is actually rather surprising, right? Because you don't have to look at each possible element, and you get an error that is relatively small compared to the range in which the sum is supposed to lie. Okay. All right. So what is the answer for this? So the natural idea, which maybe all of you know, is sampling. So what you would do is, so the algorithm for this could be sample, in this case, some k elements. So now when you say sample, the question becomes with replacement or without replacement. Okay. So it turns out there is a difference here. So with replacement. If you want to sample without replacements, then the analysis becomes a bit more messy. Okay, so sample the element with replacement, and compute sample and rescale by factor. Because you want to compute the sum, right? So if you wanted to compute the average, just the empirical average would have been the same. But if you want to compute the sum, you compute the sum of the sample and then you rescale by n by k because you sampled k. Okay, and there were n2. So firstly, how many of you want me to explain what it means with replacement? Anybody? Okay, so with replacement basically just means that you pick an element and then if you want to sample the next time, you include that element also. So don't ignore that. Yeah.
Just to see if my understanding of why is right.
Yeah.
Really, when we're sampling, we're trying to estimate distribution, right? And so if we did it without replacement, then it would kind of skew what the distribution is.
No, so just for the expected value, it turns out that even sampling without replacement is fine. It would, yeah. So actually, you will see that in your homework. It's just that proving something about it will be a bit more messy. So even with like 3 elements, it turns out that you have to do a slightly more involved sum of stuff because, right, like you are saying, right, like you might imagine that it can get skewed in weird ways, but just because of symmetry, it will not. But you have to do a computation to see that it works. Yeah.
Is this true for is this correct for all standard or?
Yeah, so it's we will see in what sense it is correct.
Yeah.
Yeah.
If we have an array of 2 elements like -1 and 1, then
Yeah.
this would work.
Right. Yeah. So this would right. So that's what we want to get at, right? So we want to get at what does it mean to say that this is correct, and like with all randomized algorithms, here we will see that there is some notion of error, right? So there's some probability that this will be incorrect. So our goal will be to bound the probability. Okay. But is the procedure clear? So this is what you would expect is you don't have the patience to go over all of these things, so you randomly sample and you hope that this is a good estimate for the sum. All right. So this is the procedure. And these are the questions we'd like to understand. Okay, so basically what people have been asking is that how bad can your error be? Okay, so can you always bound it by 0.01 n, for example? And how many samples do you have to choose? And with what probability that, what confidence do you have that your bound is correct? Okay, that's the kind of stuff we will see. Okay, and these are also called confidence intervals that you've seen. You've taken some statistics class, same thing. Okay, so these are okay, and what you see is that there are trade-offs between all of these quantities, which is the number of samples, which we call k, and the error in the result. And intuitively, you expect that if you take more samples, the error will be smaller. Okay, so and the confidence in the result is the same thing, right? So more samples implies okay. So you have actually error in result kind of captures the confidence, right? Like you say that you have an error only if you are confident that it is only that error. So that's what this is. Okay, so these are the key quantities that will come up. So I think this is a good time to stop, even though we have a couple more minutes. So let me stop here, and next time we will see a bit more about sampling, and then we'll basically conclude randomized.